Okay, let's just cut straight to the chase. We all know that System 1 versus System 2 idea in human thinking, right? The whole Daniel Kahneman framework.
Yeah, the fast gut reaction versus the slow, deliberate thought process.
Exactly. System 1 is the instant answer. System 2 is when you stop, you think it through, you reevaluate. And for years, it feels like LLM development has been totally obsessed with building a better System 1.
Just making the gut reflexes better and faster.
Right. But the whole frontier has shifted now. We're seeing this massive pivot towards enabling System 2 in these models, giving them time to actually think when they get a prompt, not just during training.
And that is the absolute core theme of the research we're looking at today. It's not just about how big the model is anymore. It's about how it spends its compute budget during inference.
And to really anchor this deep dive, we are unpacking a paper that just hit the servers. I think it was December 1st, 2025.
That's the one.
It's titled The Art of Scaling Test Time Compute for Large Language Models by Agrawal, Sengupta, and Chakraborty.
Mm.
And honestly, this feels like the engineering manual we've been waiting for.
It really is. I mean, until now, this idea of test time scaling, or PTS, it's been a bit of a dark art. We kind of knew that things like chain of thought or voting on answers worked, but we didn't have a really rigorous scientific grasp of why.
Or how to pick the right one for the right job.
Right.
We saw, OpenAI's O1 series doing reasoning, but for the open source world, a lot of it was just based on intuition. This paper, it changes that. It's systematic.
And the scale, that's the first thing that really jumped out at me. They didn't just run a few hundred prompts on one model.
Yeah.
They tested 8 different open source LLMs. Everything from the smaller 7 billion parameter models all the way up to the 235 billion parameter giants.
And they generated over 30 billion tokens. 30 billion across 4 different reasoning data sets.
Which is so crucial. In this field, small sample sizes can be incredibly noisy.
Oh, completely. But when you have 30 billion tokens of data, you're looking at real, actual signal, not just, random luck.
Precisely. And they use this massive data set to compare all these different TTS strategies. Things like best of n, beam search, look-ahead search, you name it. They really wanted to see what moves the needle.
So let's get into the findings then. A core idea is that inference isn't just one shot. You can spend more compute to get a better answer. But the paper's first big takeaway is what they call the no silver bullet rule.
And this is such a critical wake-up call for engineers. There's this tendency to just assume that the most complex, most expensive method, a huge tree of thought search or something, is automatically the best.
And the data says?
Absolutely not.
Right. And they found that a strategy's effectiveness is completely tied to the model you're using and how hard the task is. For example, let's talk about best of n. This is basically majority voting.
It's the simplest way to scale. You just generate, say, 64 different answers in parallel, and then pick the most common one.
And for a lot of the models they tested, especially the smaller ones in that 7 to 14 billion parameter range, best of n often beat the more complex sequential methods.
Which is so counterintuitive. You'd think a sequential search where the model explores a path, realizes it's wrong, backtracks, and tries something else would be smarter. It feels more human.
It does. So why does the brute force generate a bunch and vote method win out?
It all comes down to the reliability of the verifier. So in any of these strategies, you have 2 parts. The generator creating the answer and the verifier grading it.
Okay.
In a sequential search, you're making step-by-step decisions based on the verifier's signal. The verifier says, this step looks good, keep going.
So the model commits to that path.
Exactly. But here's the catch. If your model is small or just not well-tuned for verification, that signal is really noisy. It's like having a bad GPS that's just slightly off at every turn.
A smart sequential route would just confidently lead you off a cliff.
That's the perfect analogy. Whereas with best of n, you're basically just buying 100 lottery tickets. You generate 100 completely independent attempts. Even if your verifier is mediocre, it might be just good enough to spot the winning ticket in the pile at the end.
Even if it wasn't smart enough to guide the process step by step.
Exactly. And the study shows that as the models get bigger, when you move up to that 235B parameter range, their internal verifiers get good enough that the more complex strategies start to really shine. They can actually handle the nuance.
Which leads us right into their second big finding, which I thought was fascinating. They categorize reasoning tasks into short horizon and long horizon traces. And this isn't just about how long the answer is it?
No, not at all. It's about the logical depth. How many dependent steps are there? A short horizon task could be a math problem with, say, 4 or 5 very clear logical steps. The path is pretty straightforward.
Like the GSM-8K dataset, the grade school math stuff?
Correct. But then you have long horizon tasks like really complex code generation
Mm.
or the hardest problems in the math dataset. In those cases, the model might need to generate dozens of lines of reasoning, where line 20 is completely dependent on line 3 being correct.
And that's where this trace quality metric they came up with gets really important. They found that quality degrades very differently depending on the model.
Yes. For the smaller models, the chance of any single step being correct just drops off a cliff as the chain gets longer. It's an exponential decay. If a 7B model has, say, a 90% chance of getting one step right, after 10 steps, the odds of the whole chain being right are, well, they're not great.
It's about 34%, roughly.
Right, so for these long horizon problems, just telling a small model to think longer or to generate a huge chain of thought can actually make things worse. You're just giving it more chances to go wrong.
So the magic prompt, let's think step by step, isn't always so magic.
Not for every model, no. The paper shows that the bigger models, they maintain their trace quality much better over these long horizons. They have the, you could call it working memory, to hold the context from line 1 when they're writing line 50.
That distinction really complicates the picture. It suggests that if you're building an app, you need to almost classify your queries first. Is this a sprint or is this a marathon?
And that leads to their third trend, which is honestly the most optimistic part of the whole paper, the budget equation. They found that despite all these complexities, if you do pick the right strategy for the job, performance scales monotonically with your compute budget.
Monotonically,
Right.
meaning the graph just keeps going up. There's no plateau.
We haven't hit the ceiling, at least not in this study. In traditional ML, we always worry about diminishing returns. You double the training data and get a tiny 1% bump. Here, with inference-time compute, the returns are remarkably steady.
So if I'm willing to spend, say, 100 times more compute on one single answer by generating thousands of candidates or running a huge tree search, I can essentially buy a higher IQ for that specific query.
Yes. The paper establishes what they call a compute optimal frontier. It shows for any given budget, there's a maximum accuracy you can achieve. And crucially, that frontier is still rising at the very edge of what they tested.
Which brings us to the most actionable part of this whole thing, the practical recipe. The authors didn't just give us analysis, they basically wrote a guide for engineers. I think we should spend some time on this.
Let's do it.
Okay, let's play this out. I'm an engineer at a startup. I'm building a coding assistant that has to solve complex debugging problems. So that's a long horizon task. I've got access to a Llama 370B model. How do I use this paper's recipe?
Okay, so step 1 is what you just did, problem difficulty assessment. You've identified it's a long horizon task, so the paper suggests for these harder, longer problems, simple parallel sampling, the best of n method, it starts to lose its power.
Because most of the samples I generate will just be garbage anyway, right? Because of that trace decay we talked about.
Exactly. You generate 100 code snippets and 95 of them are just broken.
Mm-hmm.
So step 2 is model capability. You're using a 70B model. In their study, that's in the medium to large category. It has pretty decent verification abilities, better than a 7B, but not quite as solid as a 235B model.
So I can trust it to check its own work, somewhat, but not perfectly.
Correct. So step 3 is the compute budget allocation. The recipe suggests that for this specific combination hard task capable model, you should lean towards a sequential strategy. Something like a modified beam search or a tree search.
Not just blasting out parallel samples.
Right. Because you need to prune the bad branches of reasoning early. You want to use your budget to figure out when the model is going off the rails before it wastes time and tokens finishing a bad answer.
But hang on, isn't sequential search just slower? I have to wait for step 1 to finish before I can even start step 2?
It is slower in terms of latency, of wall clock time, but it's more compute efficient in terms of the total tokens you generate to get a single correct answer.
Ah.
So if you have a strict latency requirement, like the user needs an answer in 2 seconds, you're forced back to parallel sampling.
Huh.
But if you want the best possible answer and you can wait, say, 10 seconds, sequential is the way to go.
That's a huge trade-off, latency versus total compute.
And the paper really quantifies this. They show that just cranking up the n in best of n eventually just flatlines. You exhaust the model's diversity. It just keeps giving you the same wrong answers over and over. Sequential search forces it to explore different paths.
Okay, let's flip the scenario then. What if I'm using a much smaller model, a little 7B parameter model, on a relatively easy math dataset?
In that case, the recipe completely flips. That 7B model has a very weak internal verifier. So if you try to make it do a beam search, it will probably misjudge the intermediate steps and accidentally prune the correct answer.
It overthinks itself into a corner.
Precisely. So for a small model on an easier task, the paper's recommendation is clear. Pure parallel sampling. Best of n with a simple majority vote. Don't ask it to critique itself step by step. Just ask for 20 different answers and take the consensus.
This is so different from the old one prompt to rule them all mindset. It really treats the model as one component in a much larger system.
That's the paradigm shift. We're moving from just prompt engineering to what you could call inference system engineering. The LLM is the engine, but you still have to build the transmission and the chassis around it.
There was one other detail in the recipe I wanted to touch on, the verifier. The paper mentions that for the absolute best performance, you might need a separate process reward model.
Yes, that's the gold standard. A process reward model, or PRM, is a totally separate model that's been trained specifically to score the steps of reasoning, not just the final answer.
So the bottleneck shifts. Eventually, your generator is smart enough to create the right answer, but your verifier isn't smart enough to recognize it.
That's it exactly. And that's probably where the next frontier of this research is headed. If we want to keep riding that monotonic scaling curve, we're going to need verifiers that are significantly smarter than the generators are grading.
It's almost like the P vs NP problem, but for AI. It's easier to check a proof than generate one, but checking a partial proof is still incredibly hard.
And this paper really exposes that. It gives us a map of where we are today, but it also points right to the cliff edge where our current verifiers just stop working.
So, pulling it all together, we have a study that validates this System 2 approach. It gives us a recipe for picking strategies based on difficulty, model size, and budget. And it proves that at test time, compute can be directly converted into intelligence.
It fundamentally changes the economics of how we deploy AI.
That's exactly where I wanted to end up. Because economics isn't a metaphor here, is it? We're talking about actual cost. If the graph keeps going up, if better answers are always available for more compute, then the truth just became a variable cost product.
It did. It means the quality of an answer you get isn't fixed by the model's weights anymore. It's determined by how long you can afford to let the meter run.
And think about what that means for you, the end user. Right now, we sort of assume two people ask an AI the same question, they get a roughly similar quality of answer. But if test time scaling is the new standard, that all changes.
You could see a tiered reality. The premium user gets the long horizon, tree search, 10-second compute answer. It's nuanced, it's error-checked, it's highly accurate. The free user gets the System 1 gut reflex.
It creates a whole spectrum of information quality based entirely on who is willing to pay for inference cycles. We're not just gatekeeping access to the model anymore. We're gatekeeping the depth of thought applied to a problem.
And for really critical tasks, medical diagnosis, legal analysis, scientific research, that difference in thinking time could be the difference between a major breakthrough and a subtle hallucination.
It's a fascinating, if maybe a little daunting, future. But at least, thanks to Agarwal, Sengupta, and Chakraborty, we now have the data to start navigating it. We know the trade-offs, and we have the recipe.
The black box is a little less black today.
A huge thank you to the researchers for this incredible contribution, and thank you for helping me break it all down.
My pleasure.
And to everyone listening, the next time you see that loading spinner on your AI prompt, just remember, it's not just lagging, it's climbing the compute optimal frontier. We'll see you on the next deep dive.